Yes. No screen here. What happens here?
So I have a question for homework 6. What's the example 3.7 bioassay experiment?
3.7.
Bioassay.
Yes. It was addressed during the class. I don't remember exactly, but like fifth or sixth lecture, it was addressed to the students. And also it is in the Gelman's textbook, section 3.7.
Do you want the computer on? Here's a
Sorry, I didn't do this.
there you go.
I make many mistakes today.
No problem.
I have to address for today's lecture about the correlated version of regression model. And I believe that this is much more complex than the previous ones that you learned in this classroom. That means that I also have a difficulty to teach this topic to the students. And I have to try myself. In order to let you understand this, I'd like to give you some basic understanding what the correlation is. We need to understand this concept in order to move to the regression model. And I'd like to talk firstly about the multivariates, normal distribution. And in order to do that, remember that we already familiar with the normal distribution. Normal distribution, in case of a single parameter, normal distribution, we have two parameters, mean and variance. Once we have these two parameter values, we have everything for that distribution. We can analyze that. We can also draw the plot of that distribution, which is normally distributed. In case of more than one parameters, similar things. We need to have, in that case, we need to have a vector of means. In case of two parameters, we need to have a variance of each parameters in the form of vector. And also one more thing we need is the covariance of the two parameters or multiple parameters. Because of this, there is a difference between the ordinary single parameters and the multiple parameters. And in order to efficiently describe this distribution, we introduce the matrix denoted as capital sigma. And the capital sigma includes, on the diagonal terms, the variances. And on the off-diagonal terms, the covariance. And this can be easily understood by the case of two variables, two parameters. In case of two parameters, the covariance matrix is given in this form. You see here the diagonal terms, the variances of each parameter. And the off-diagonal parts describes the covariance of any two parameters. Because this is only two-dimensional example, we have only one off-diagonal term. But if it's more than two, you will imagine what happens in the matrix. And at this moment, I'd like to make you understand, distinguish the meaning of a covariance and correlation. Normally, these two terms are used exchangeably. But strictly speaking, the covariance is a term what we put here. On the other hand, the correlation, this is a non-dimensional value, which is divided by respective standard deviation. So in this case, you see here rho. This represents the correlation, or more exactly, correlation coefficient. And all these multiplication represents covariance. You can see the difference between these two. And the matrix here, we say this as a covariance matrix. So by introducing this matrix notation, we define the multivariate normal distribution in this way. In this case, we have a vector of mean values for the parameters, one of the parameters, and the other, the matrix of a covariance, capital sigma. And the resulting expression is given here. You can compare this with your familiar expression for the single parameter version. I hope you already familiar with this expression, single parameter. Compare this and this. You can compare this with this one. And you think the capital sigma is simply the generalized version of a single parameter variance. So put this in here. Inverse square root turns into the 1 over sigma. And the inverse of this matrix turns into here, the denominator. You can compare the difference between these two. Also the similarity. And this is the single parameter. If we move to the multiple parameters, but with independent distribution, in that case, we just have the covariance matrix with only the diagonal terms, because if there is no correlation or covariance. In that case, also we can make from here to here quickly by some hand manipulation. You get this result. So along this direction or the expressions, you need to understand the meaning of this one. I'd like to illustrate what the correlation is using this example. This example considers only two variables, and the only two variables is sufficient to explain. And you can generalize this understanding to more than two variables. And we have two x1 and x2 parameters, and this follows the multivariate normal distribution with the mean at here, with the covariance matrix at here. And you see the variance of each parameter is units, 1. And we have a correlation rho. In this case, we'd like to simulate x by drawing samples with this number of samples. So at the end of this process, we will get the 1,000 number of vector x. When there is no correlation, like rho equals to 0, then this is the same as the sampling x1 and x2 independently. If you did correctly the homework throughout this course, you already know how to do that. Draw 1,000 sample for x1. You can do that. You can imagine in your head. Independently, you can make 1,000 samples for x2 when there is no correlation. Then you already got the solution. 1,000 samples of x1, 1,000 samples of x2, pair that. Then that is the solution. And this is the result. You can also do the same thing by convenient MATLAB function with rho being 0, the same thing. But the result is the same. Whenever you do the independently or use this one with rho being 0, we get the same result. Because there is no correlation, we have the scatter plot like this, like a circular shape. This is the result of 1,000 samples. Let's move to the case of correlation. If we have the correlation to some degree, like 0.5, what we get from this simulation is this graph. If we have more stronger correlation, we move to here. And as an extreme case, if the correlation is 1, we get that result. And you see this trend. As we have more and more correlation, the scatter plot is moving from here to here. And this represents if we have a higher value for the x1 sample, then it is highly likely that the x2 will also be, the value will be higher. That represents the correlation. So this is the meaning of this correlation. And based on this, we'd like to move to correlated case of regression. This is Gelman's remark, the remark in the textbook. According to that, previously there were a number of assumptions in the ordinary regression, which are, we assumed linearity of the response. We assumed normality of the error terms. We assumed the normal error follows normal distribution. And the third, we assumed independent observations with equal variance. And he says none of these are true in practice. And among these, I'd like pay particular attention to this one, independency of the observations. This at first seems to be reasonable, but soon I found that this cannot be reasonable. Consider the error. We have the data, and we have the regression equation. So it is always something like data and the fitting. And we have the error. And according to this correlated regression, they say that the error at a point here, the ith point, when the error at the ith point was -1, then the error at the very next point cannot be +1. it's nonsense. According to the concept of correlation, this is against the common sense. That means if we have some observational error at here, the very next point observation error cannot be here. It should be somewhere around, not much difference from this value. That is the necessity of introducing correlation in the regression model. So if we ignore these features during the process of the regression analysis, then we will get to the wrong results. So we need to incorporate that thing into the regression. And because the equations that we will deal with is very complex, we need to review the equations that we made in the classical regression here. I don't do this one more time. I just show you this will be playing important roles in the subsequent derivation. So I just show you here. This is the results of classical regression. Also, this is the results of the Bayesian version of the ordinary regression. For this, I have already explained Friday last week, just 3 days ago. And what I said was about the joint posterior PDF in case of very simple example, which was in which the regression model is given by this linear equation. And these two, beta 1, beta 2, are the unknown coefficients to estimate. And also there is the error between the data and regression. All these coefficients or parameters are unknown to us. And based on the observed data y, we'd like to estimate these parameters. And the result is this, the posterior distribution. And I hope you remember what the capital X means. Capital X is the matrix. The first column consists of only 1, and the second column is the X values of the data points. So we have this expression, then we can sample by whatever means, like Markov chain Monte Carlo, or even based on the analytical procedure. Only in this case, we can make samples. If we would like to consider correlated case, we need to start from the likelihood to obtain the data y based on this information. And this information is given by the multivariate version. This is contrasted with the previous one. This is the ordinary regression, result of the ordinary regression. This is the correlated case. Always compare and look the difference and the similarity. In the ordinary regression, we had always the same variance, which is unknown, over each data point. So in that case, it was only the diagonal matrix. Now we have the correlated matrix. Only the difference is this. And the expression is turned from here to into here. And this is the covariance matrix I introduced already. So apply this into the posterior distribution, we get the results for the unknown parameters. Before doing that, most of the times, the covariance matrix, capital sigma, is conveniently represented by this form. The covariance matrix can be decomposed by a scalar, sigma square, and non-dimensional matrix. I see this is a correlation structure matrix, Q. Using this, we can reduce the unknown parameter from the general covariance matrix to a single sigma square in the Bayesian procedure. And I'd like to address what the Q is and what behavior Q shows us. Because Q is expressed in this function, which is the exponential and minus the difference over 2 points divided by some parameter d and square. So if the I and j, the 2 points, agree, then it means we have the value of Q being 1. And if the distance of the 2 points is increased, then we have a smaller value of Q. So Q is the maximum with the value 1 at the diagonal, and it decreases as the distance between the 2 points increase. We can draw the shape of Q by making this into this expression. And as a function of x, we can draw the shape, and we get this. And if d, another parameter d, is small, we get the blue curve, the narrow shape. If d is large, we get the shape like this one, the wider shape of the correlation. Based on this, we can also make the matrix for the case of the x at the range of 0 and between 0 and 1 with the interval 0.1, we can construct a correlation matrix. At the most left side, the value is at x0, and the rightmost side, the value is x at 1. And in between, x varies with the interval 0.1. And we can see the shape of the matrix in this form. The diagonal part always, the value is 1. And the off-diagonal part is given based on this expression. And if the value d is very small, the value quickly decreases to almost 0. So in this case, the blue color represents it's close to 0. If the value d increases, the shape of this matrix changes in this way. And if the d value is much higher, we have almost the same value over the matrix domain, which is near 1. And I always made the things that I did here in the MATLAB code, so you can get help from that as well. Using this example, I'd like to explain what the correlated y means. I'd like to introduce a y which follows multivariate normal distribution, but the mean is always 0, and the covariance matrix is given here, like the one that I explained just before. And we'd like to simulate y, which is a function of x, but the mean is always 0. Only we have the covariance matrix like this. So we'd like to simulate, make samples of y over the range of x between 0 and 1 with the interval 0.1. We will make only 4 samples, 4 y's, instead of 1,000 samples, in order to illustrate what the correlation means. And at first, when there is no correlation, it's simply the diagonal matrix here, and it's simply making independent sampling at each point x. So let's start at the point x0. We made a value y here by a random generation of a normal distribution. At the next point and next point, every point we make a random y, realized y, but each point is not dependent with each other. So when we have this value of y here, at the very next point, it doesn't have any relation with the previous y. As a result, you will get some kind of a zigzag shape because of their independence. Let's move to the correlated case. If we have a correlated structure for this matrix, we can start with this point and moving to the very next point. In this case, we have a little correlation. So we cannot have the new y at somewhere around here because of their dependence, because of their correlation. So we have to move somewhere not far from here, and the result is here. And this is continued all the way to the end of the interval. So this is the result of the first simulation. By this way, I made 4 arbitrary samples of y here. As we increase the correlation to a higher value, we get the trend like this. And at the extreme end, what we get is when we start from an arbitrary value at here, there is no other freedom. Because of extreme correlation, we have to have always the same value at the initial one. So you can compare this extreme case and this extreme case and in between. And by this way, I hope you may understand the meaning of correlation.
Is there any requirement for the choice of x? Should it always be within 0 to 1?
Oh, this is just for the illustration.
If there is no specific requirement for x, then the parameter d seems to be redundant. I mean, you can always rescale the x to remove the necessary of having a d.
So your question is removing.
I mean, why there is a parameter d there? So I can simply choose the xij to control the qij matrix instead of having both of them.
I'm sorry, I didn't quite understand your.
I mean, so if the x should always be within 0 to 1, then it is quite clear that I need to have an additional parameter d to control the value of matrix qij, right? But
Yes, in order to control the smoothness of the y over this range represented by this way, we need to introduce the parameter D. D controls the shape and the level of correlation throughout this range.
I think that I understand the question. D is the distance at which the correlation decays as 1 over E. So it's about 40% or so. So if X didn't vary between 0 and 1, the meaning of D equal to 5 will be different. And what matters is the ratio between D and the range of X. That is, if the ratio is 5, it means it decays very slowly, while if the ratio is 0.1, it means the correlation decays almost instantly. So you always need D, but the meaning of its value depends on how it compares to the range of X.
Mikey.
So I'm curious about the terminology. So for uncorrelated case, we call sigma noise. So how do we call sigma for correlated case?
Still, in uncorrelated case, we introduce sigma as the in the ordinary regression as the error of between the data and the regression. In the correlated case, the meaning of the sigma is still the same. It represents the level of the difference between the data and the regression.
So basically sigma represents the error between the prediction and the true function.
Yes. Unknown true function. We don't know the true function at all. We only have the data, and we just estimate it. Yes. Yeah, I'm getting more and more to the complexity of the expression. And this is the thing that I tried to let you understand. Based on the introduction, in the case of a multivariate version, the likelihood was expressed in this way. Remember, this is the newly introduced matrix, covariance matrix, and this is the likelihood. And based on the textbook derivation by Gelman, he introduced the Cholesky factor for a matrix. Based on that, the matrix can be decomposed into its upper and lower triangular matrix. And I also introduced what it means in the MATLAB code. Every arbitrary matrix can be decomposed that way. Once we have that decomposition, this can be applied here. You just imagine in your head, put this in here, and distribute the left one into the left terms and the right one into the right terms. Then you get here. So until this moment, it is not that difficult to get this. And soon we will find this is the same as the, by comparing this expression with the result of the ordinary regression, you will soon realize that the y and capital X of the classical regression is turned into this and this, and we will get the same results. In order to have more a better understanding, it is advised to make derivation by the students. So I just show you only the result here by omitting the full derivation. The result is simply replace this by this one in the result of the ordinary regression. Then we get this result. And remember that the capital sigma was also given in another form like sigma square and q. So when we have Cholesky decomposition, it is talking about this one. And by going through the derivation, we obtained this distribution. And if you had any difficulty, you just look at this one. And you use this distribution to make samples of beta, of sigma, by whatever ways. The easiest way that we can take is the Markov-Chain Monte Carlo. Use this and make samples. Then you finished. You got solution. And in order to have better understanding, I suggest you to understand how this was derived. That will make you a better understanding. But if you don't understand that, you just use the result, this, using a sampling method. I did it already by using the sampling methods. I obtained the 5,000 samples of beta 1, beta 2, and also sigma square. The same thing was went through in the case of ordinary regression. And in this case, it's a multivariate correlated regression. And I put the value, the correlation parameter. Within this, we have the correlation parameter. This was the thing. This was the definition of the correlation matrix Q. By using D with this value, I made the 5,000 samples of beta 1, beta 2, and sigma. Then everything is finished. The thing left is to make a posterior prediction. But in the case of a posterior prediction, we have much more complex case. It is quite different from the ordinary regression. If we need to have the prediction, we still need to incorporate the existing data, existing observations, unlike the ordinary regression. This can be explained by these facts. For example, if we wish to predict the height of a new child, whose brothers already exist as the old data. So in this case, the brothers, existing brothers, play the role of existing Y. And the new child is something like a new Y. And we cannot do this independent of the existing Y. Then we have to construct the likelihood in this form. This is another difficult point for the students to understand. And we can manipulate this expression to obtain the equations at the bottom. I already explained the case of two parameters for Gibbs sampling. I hope you remember this part. In the case of two parameters, at that time, the emphasis, the point was on the two parameters, not the correlation. But already I addressed the correlated case at that time. And although I did not explain the thing, quickly I moved from here to here based on some kind of a formula or equation. This means a conditional distribution of theta 1 based on theta 2 and vice versa. And how did we get from here to here? It's not easy, even in the two-parameter case. In the Gell-Mann's textbook, there is the formula at the end of the textbook in the appendix, like this. And this was made from this relation. Now, how did we get these results? This is beyond our ability. We need to make some more understanding of the statistics. In the exactly same way, from here to here, we use this relation. So the relation here, you compare this. And for this equation, you compare this. You will see the very much similarity between the two. So by applying this into the prediction, we get this equation. And we have 1,000 or whatever number of samples for beta and sigma. We can apply each individual value here, get also the 1,000 samples for nu y, the mean and variance, and plot it, as I did in the ordinary regression. And the results are, surprisingly, in the case of a small correlation, we have these results. As we have the higher value of the correlation, we move here to here. And you can compare the results with the ordinary regression. Yes?
So to solve the regression, so are we assuming that the covariance function, that is the value of d, is known, or we don't know the covariance function?
In the case of correlated regression, we need to introduce some kind of this. This is only a specific example among many others. Even there is a case, not a 2, but another value. So, in this case, when we introduce d and we put some specific value for d, we get these results. But in the Bayesian version, even this can be treated as the unknown using the Markov chain Monte Carlo.
So how can we identify the value of d?
In this case, I just used a certain value by trial and error. And if we are not satisfied with that, we don't have any knowledge on d, we put this into the unknown and let the Bayesian determine. So we have some discussions on this posterior prediction. Based on this prediction formula, it always interpolates the observation points based on this derivation. Anybody with this level of knowledge, like you will understand what this means. You will follow, and lead to the get to the conclusion that the new y always agrees at the observed data, even with the prediction equation. And the variance is also vanished at the observation point. And the choice of correlation factor, D, is important in characterizing the uncertainty of this regression, correlated regression. And if we have a small correlation, as the Professor HAFTKA said, it quickly vanishes as the distance is larger. And it is very, if the correlation is very high, D is, the value of D is increased. And we get this result in case of high correlation. So when we don't have any knowledge or intention for D, we can also put this into the unknown in the Bayesian estimation. Then we have one more unknowns. Previously we had beta 1, beta 2, sigma 3. Only 3 were unknown. And in this case, we can add one more parameter. And let the Markov chain Monte Carlo compute this. Still have the 5,000 samples we can make. And incorporate this into the posterior prediction. And we got this result. This is the results when we have no knowledge on D. And this is compared with the case of when we put some specific value. I will explain some more in the next class, which will be a month later. I will address one more time about this at that time.